Hello everyone. In this video, we discuss parametric models for classification problems. Parametric models for classification problems are very similar to parametric models for regression problems, including linear regression or polynomial regression that we discussed previously. However, there is a very important difference. And that's because in classification problems, our goal is to predict discrete targets, or outcomes that we usually refer them to also as labels. To explain these differences, we start this discussion by going through logistic regression and focusing on problem formulation, assumptions, loss functions, and finding gradient. And then in the second part of this video, we discuss logistic regression in scikit-learn and how you can implement it. So what is logistic regression? Logistic regression is a probabilistic model that can be viewed as the probability of y, and y is our target or label, given the input vector x, which we assume is a d-dimensional vector, and some unknown parameters theta. So the goal here is to find this theta. Once we find theta, we know this probabilistic model and we can make predictions. In general, we have two types of classification problems. Binary, which means that we only have two classes. So this C, which is the number of classes, equals 2. And in this discussion, we assume that Y is either 0 or 1. Then we have C greater than 2. That's why it's known as the multi-class classification problem. And in that case, we usually assume that Y can be anywhere from 1, 2 to C. So we have C distinct labels. In general, these labels that we use here are mainly to distinguish between data points from different classes. So they do not have numerical values. And that's why usually for binary classification, we use 0 or 1 or -1 and 1. And for multi-class classification, we usually use 1, 2 through C. So in order to explain the logistic regression model, we need to first remember the probability mass function, or PMF, for a Bernoulli random variable. And why do we want to do this? So remember, Bernoulli random variable explains a binary random experiment, meaning that a random experiment can have two possible outcomes. And in this case, let's say one outcome is 1 and the other outcome is 0. In this case, we really need to know the probability that the outcome is 1, because the other probability using the complement rule is 1 minus theta. And you can see that if we add these two probabilities, we get 1. Therefore, Bernoulli distribution is very, very important for understanding binary classification problems. And usually in machine learning, we like to write things in compact forms, and it appears that we can do this for Bernoulli distribution by writing this as theta raised to the power of y, 1 minus theta raised to the power of 1 minus y. And why is that? So if y equals 1, then you see that we get theta raised to the power of 1, which is theta. On the other hand, 1 minus 1 is 0, which means that the second term will be 1 minus theta raised to the power of 0, which is 1. And overall, we get theta times 1, which is theta. And the same thing happens when y equals 0. In this case, we have theta raised to the power of 0, which is 1, and then 1 minus theta raised to the power of 1, which is 1 minus theta. So here is the very compact form of Bernoulli distribution when y can take on two possible values, 0 and 1. So what is the connection with logistic regression? So this probabilistic model that we said that is the main form of logistic regression can be written as the probability mass function for the Bernoulli distribution, where this parameter that we have that determines whether we get 1 or 0 is in this form of the sigma of f of x and theta. To explain this function f will find a linear combination of the input features, very much similar to linear regression. And you can assume that this is simply the dot product between x and theta, the input feature vector and the model parameters. However, the key point is that this probability parameter, this theta, should be between 0 and 1, right? That's the main requirement when you're working with probabilities. And for that reason, we use this function, which is sigma, known as the sigmoid or logistic function. This sigmoid function has this form that for any number a is 1 over 1 plus e to the negative a. And the nice thing is that for any real valued a, the result of this function is always, or the range of this function is between 0 and 1, which is a valid probability score. In the next cell, we're going to plot this to show you that this is indeed a valid probability score, and it is between 0 and 1. But we'd like to emphasize here that the way that this probability here works is that first we find a linear combination of input features, and then we apply the sigmoid function. So in fact, it's a composite function. So in order to plot this function, we import NumPy for numerical arrays and matplotlib. And here I'm assuming that I want to plot this function for values of a from negative 10 to 10. And the sigmoid function is 1 over 1 plus e to the negative a. And so here we can see that at a equals 0, this function is 1 over 1 plus 1, which is 1 over 2. So that's where we get 0.5. And we have two horizontal asymptotes. One, as this a goes to infinity, you can see that this reaches 1. And on the other hand, when a goes to negative infinity, this goes to 0. So that's a very nice thing about this sigmoid or logistic function, because regardless of what the input value a is, the output is always somewhere between 0 and 1, which can be viewed as the probability that we have in the probability mass function of a Bernoulli distribution. Well, here you may say that, well, there are multiple or many functions that can have this range from 0 to 1. So why is it so special about this logistic function? So one very nice property of logistic function is that its derivative, which is very important because we always work with derivatives and gradients in machine learning, has a very simple and nice form. So the sigmoid function is 1 over 1 plus e to the negative a, which we can write it in this form. And then we can use the chain rule to find the derivative of this respect to a, which we get negative 1, and then this term raised to the power of negative 2, and the derivative inside here, which is this term we have here. And if we simplify this, you can see that we can write this derivative as 1 over 1 plus e to the negative a times e to the negative a over 1 plus e to the negative a. And the first term is exactly the sigmoid of a, which is the definition that we had here. And you can also see that if we have 1 minus sigmoid of a, then we get this second term. And this is very interesting about this function, because if you take the derivative of the sigmoid or logistic function, we get the sigmoid function times 1 minus sigmoid function. So let's look at the derivative of this function and see how it looks like. So here is where we plot the derivative of the sigmoid function, sigmoid of a times 1 minus sigmoid of a. And so you can see that the red curve here is the derivative. So the max is achieved at 0. And then since we have these two asymptotes at 0 and 1, we can see that the derivative approaches 0. So this is the general form of the sigmoid function and its derivative. But this sigmoid function also has some other properties too. So as we said, the sigmoid function gives us the probability score for a Bernoulli distribution. So this means that under this assumption, we can assume that the probability that y equals 0 in a classification problem, in a binary classification problem, is this sigmoid of A, which is 1 over 1, 1 over 1 plus e to the negative A. And we can multiply both numerator and denominator. Here we have probability of y equals A given x and theta is the sigmoid of A, which is 1 over 1 plus e to the negative A, and we can multiply both numerator and denominator by e to the A to make it a little bit simpler. And therefore, the probability of y equals 0 is 1 minus this sigmoid of A, which is e to the negative A, 1 plus e to the negative A. Similarly, we can multiply both numerator and denominator by e to the A, and we get 1 over 1 plus e to the A. And here's the very nice thing. If I divide this probability of y equals 1 by y equals 0, then these two terms cancel and I get e to the A. And now if we take the logarithm of this, then we get A. So what we did is that we did this division, we took the log, and that's A. So therefore, what this means is that this A, which is the input to the sigmoid or logistic function, can be inverted if we know this probability of y equals 1 and y equals 0. And this is what is known as the log odds or logits. So to simplify this, when we have a sigmoid or logistic function, what goes inside this function, which is this A, is known as log odds or logits. So this is a real valued number. And then after that, we get the output of the sigmoid or logistic function, and that's something between 0 and 1, which we think of that as this probability of y equals 1. And this inverse of the sigmoid function actually has a name, which is called the logit function. So the logit function, if we have this probability p, is log of p over 1 minus p. We use this notation, usually logit, to show this. And here's a summary that I just mentioned. So when you have the sigmoid or logistic function, it's an invertible function, and it allows us to get any continuous number A and convert this to the probability space, which is from 0 to 1. And then we can get this probability back into the corresponding log odds or logit space using the logit of P. So let's look at both function, the logistic function and logit function. So these things are implemented under the SciPy library. So you can obviously write your own functions, define your own functions in Python, but because these are very important functions that are already in SciPy. And this expid, this is the sigmoid or logistic function. And the second one is the logit function. So we're going to plot both of these. First, we're going to plot the sigmoid or logistic function, and then the inverse, which is logit. So if you look at this, the one on the left is what we're familiar with, right? So the x-axis can be any real valued number, and we know that for a equals 0, this logistic function gives us 0.5. We have two asymptotes at 0 and 1. But here's the thing with logit function, right? So here you get a number from 0 to 1 on the x-axis, so that's the input, and the output is what we call it the logit or the log odds of the sigmoid or logistic function. So at 0.5, we get 0. This makes sense because 0 is what actually gives us 0.5. So this is the inverse function. And then you can see that we have now these two vertical asymptotes. And this is very important because overall what this means is that we can take a real valued number, as you can see on the left side, and find a probability score. And we can get a probability score and convert this back to the log odds space, or the real valued number that gives us that probability score. So that's why logistic function is very important. And also this method is called logistic regression, even though it's technically a classification problem. So overall, putting everything together, we find first a linear combination of input features, apply the sigmoid function, and therefore the probability that y equals 1 given x and theta is this sigmoid of theta transpose x, which is 1 over 1 plus e to the negative theta transpose x. So this exponential here, it means e raised to the power of negative theta transpose x. The only thing that is left here is that so far we have not talked about how we can find theta. So right now we assume that if we know theta, this is the general form of this logistic regression model. But before talking about theta, let's see what does exactly theta do in our analysis here. And we can do this by talking about like the decision boundary. So what is the decision boundary? So in general, you want to know when you have a new input vector x or feature vector x, when we assign that to class 1 versus class 0, because we're talking about a binary classification problem. And in order to answer that, it's very simple. Since we have a probabilistic model, we want to have probability of y equals 1 given x and some theta. I removed that here for simplicity, but you can add theta if you want. If this probability is greater than probability of y equals 0, right? So if the chance that the data point belongs to class 1 is greater than the chance that it belongs to class 0, then we say that it belongs to class 1. And the nice thing is that we can convert this probability back into the log odds space or the largest space. How can we do this? We can divide both sides by probability of y equals 0. And since it's a non-negative number, we do not need to change the direction of this inequality. And then we take the log of that, right? So log of 1 is actually 0. That's what you can see we get here. And why we did this? Because the nice thing is that this log of these probabilities, we just talk about this, that this is what it gives us the log odds or the logit. And therefore, as you can see here, if the log odds or logits are positive, this means that we assign the feature vector x or the input vector x to class 1. And these log odds in the case of logistic regression, again, is what we call it as A. And A here is just this linear combination of theta and x. So overall, putting this back here, this means that if this inner product or dot product between theta and x is greater than 0, then we say that the label is 1. And that's exactly what we have here. And this is what is known as the decision boundary, which is defined by the hyperplane theta transpose x equals 0. If we are in a two-dimensional space, this theta transpose x is simply the equation of a line. So this means that you find a line that separates the two classes. And here is the connection between linear and logistic regression. In linear regression, you're trying to find a line that explains the data that you have, so it goes through your data. Here, we actually want to find a line that separates the data because you have two different classes and we want to be able to distinguish between them. And therefore, the geometric intuition here is that the vector theta, we have to find it, but once you find it, this determines the orientation of the decision boundary in the feature space. And then the magnitude of theta transpose x indicates how confident we are, because larger values means that we are more certain, meaning that we are further away from the hyperplane that separates the two classes, so it's less likely that we are making a mistake. However, as we said before, in order to find theta, the parameters of our logistic regression, which shows us how to do data transformation, we need to look at some suitable loss functions. And loss functions for classification problems are different than regression problems because of the fact that it's more difficult in the case of classification problems to define distances between classes because these numbers like class 0 or 1, do not have really numerical values and they're mainly used to separate classes. So in order to explain this, so remember, we always find this dot product or inner product between theta and each data point or input feature vector, which we call it an. And it's a single or a scalar here because it's a dot product. And we give this to the sigmoid or logistic function. And this gives us this probability score mu n. So the loss function, the way it works, it accepts two things. The label, which is either 0 or 1, and this probability. But how do we quantify the error here? We use something called the cross-entropy loss function. And this depends on whether yn is 1 or 0. Let's say yn equal 1, then the form of this loss function is negative log of mu n. And if yn equals 0, the form of this is negative log of 1 minus mu n. So overall, you see that the way that we penalize here, our errors are based on this negative logarithm of these predicted probabilities. But what does this exactly mean? In order to explain this, let me go first through this cell where we plot this function. So we accept y and probability mu. We are assuming that if y equals 1, then that's the form of the loss function, negative log of mu. And then if y equals 0, then the other condition that we have, negative log of 1 minus mu. And in order to have our show like different values of mu, what I do here, I assume that I have numbers from negative 10 to 10, and I use the logistic function to convert these to predicted probabilities. And then we're going to plot the loss functions for both cases when y equals 1 and when y equals 0. So let's look at the case that y is equal to 1. So why does this look like this? So remember, on the x-axis, we have our predicted probability for class 1. That's exactly that mu n that we have. So if this probability is exactly 1, and this data point belongs to class 1, then there is no penalty or cost to pay. However, as this probability that that data point belongs to class 1 decreases and gets closer to 0, the value of this loss function increases exponentially. And this is important because we want to avoid this probability to be close to 0, because that means that we are very confident that this does not belong to class 1. However, this data point belongs to class 1. So we're talking about this purple curve that we have here. And that's exactly what you see here, this negative log of mu n. So if mu n is 1, then negative log of 1 is 0. Perfect, there's no error. But you can see that as mu n gets closer and closer to 0, then this log of mu n gets closer to negative infinity, and then there's also this negative sign, which makes sure that the loss function is positive. And the same thing happens with yn equals 0, right? So in this case, we want actually mu n to be 0 because then it means that the probability that this data point belongs to class 1 is 0, meaning that if the probability that belongs to class 0 is equal to 1, so that's something that we want to do. And you can see that then for we have to use 1 minus mu n. And if mu n is equal to 1, this means that we are very confident that this data point should belong to class 1, whereas it does belong to class 0. So there is a huge penalty to pay because we get log of something very close to 0, which is approaching negative infinity, and then we have this negative sign here. And we can see this here too, right? So if you're looking at this case where y equals 0, then you want the probability that y equals 1 to be 0, which means that the probability that y equals 0 is 1. In that case, we don't pay any penalties. And as this gets closer and closer to 1, which means that the probability that y equals 0 gets closer to 0, right? So that's always considered that for the other case, we have to use 1 minus these numbers, then this loss function increases exponentially. So now we have the most important pieces of logistic regression. So in logistic regression, in the case that we have the basic linear form, we use this linear combination or weighted sum of input features. We pass this to the sigmoid function. This acts as the probability mass function for this Bernoulli distribution and gives us the probability that y equals 1. This is very helpful because now we can even understand what theta does. So this shows us the orientation of the decision boundary using the fact that this log of p probability of y equals 1 or probability of y equals 0 is what gives us the log odds space, this theta transpose x, what we have before the sigmoid function. And the loss function is known as the cross-entropy loss function, which is this simple idea that you use negative log of predicted probability. And this acts like as it is for yn equals 1, for yn equals 0, you have to just remember that that probability is technically 1 minus probability that y equals 1. So that's why we have this. So overall, this means that if you want to find the loss function over the entire training set, because what we have done is only for one sample, we can do this in this form. The only thing that I added here is that instead of having a piecewise function, like what we have here, I'll multiply the first term by yn and the second term by 1 minus yn. And we can do this because yn is either 0 or 1. It's binary. So if yn is equal to 1, then the loss function is technically this log of mu n. And if yn equals 0, then the first term vanishes and the second term is going to be log of 1 minus mu n. And then we take the average over here. And this negative sign is what we had here, right? So we have negative sign for both. So we factor that out and put it here. And then the other question is that can we compute the gradient here of this loss function with respect to the parameter vector theta? So in this course, we are not going through all the details here, but it has actually a form which is very similar to linear regression. In the linear regression case, this was x transpose x theta minus y. And remember, x is your data matrix of size n by d, and number of data points, d is the number of features, and y is in Rn. The only difference here is that actually this x theta here has to go through this sigmoid function. So this means that we do our linear combination, we apply the sigmoid function, and this is going to be a number between 0 and 1, and then we subtract this from y, and y is a vector of outputs here, which is always 0 and 1. And also this means that the partial derivatives here can be written by looking at, as you can see here, this xn transpose theta, right? Because in this case, we have to look at this summation from 1 to n of x and j's, and then sigmoid of xn transpose minus yn. So when we say x and j means that we are looking at the jth element of each xn. So xn here is the nth data point, and j is showing us the feature number. Okay, so now that we have this information, we can implement logistic regression in scikit-learn or sklearn. And the nice thing is that sklearn will automatically find this gradient for us, so we do not need to really manually define this gradient vector or each element of this partial derivatives here. And therefore, in this case, we start by looking at one of the most popular classification datasets, which is known as the iris flower dataset. So in this case, we are looking at some flowers, some of their features, such as length and width, and the goal is to see if we can correctly classify their types. So in this case, this is already part of a scale learn. So we're going to just load this data set. And if you look at it, like very similar to some other data sets that we used before, this iris here is an object which contains a couple of things, like the data matrix X. So that's exactly what we have in that. The target vector, the target names, some feature names, etc. So in this case, if I look at this iris data, so you can see that these are the input features that we have in the column. So we have 4 features: sepal length and width, petal length and width. And then we have this iris target where we have, this is in fact by default a 3-class classification problem because we have 3 types or classes. And in this case, you can see we have 1/3 of the total data. We have 150 data points in each class. We also have the names of these 3 types or species here. However, since we mainly focus on binary classification so far, so we're going to convert this 3-class classification problem into a binary classification problem by putting this condition that whether this uh, the type is this one here or not, right? So that's the essence of binary classification. So we want to answer a question with yes or no. So in this case, we don't want to necessarily distinguish all 3 types, but we want to know whether the type is this Virginica or not. And also, since the goal is also be able to visualize things here, we are looking at only one input feature, which is petal width. But in general, we have 4 features that we can use, all of them. In order to use logistic regression, we can do this from scikit-learn's linear model. And the reason that we call this a linear model is because the main assumption here is that we have that linear combination of x and theta, and then we give this to the sigmoid or logistic function. The sigmoid or logistic function does not really add nonlinearity here to the problem. The only thing that it does is to convert the result of the linear combination to a valid probability score. And we're also going to use train test split. So in train test split, we provide our data matrix, target vector, and some random number seed to make sure that we can do this consistently if we run this multiple times. And this gives us the X train and Y train, X test, and Y test. And then we can instantiate this logistic regression class to get this object, and then we do dot fit and we provide our training data. So something I want to show you here is that the output Y that we want to use here, the targets, are actually in the form of a binary classification problem because they're either false or trues, depending on whether the type is Virginica or not. And logistic regression scikit-learn is very smart in the sense that even if we provide false and trues, it knows that one is 0, the other one is 1. So it already converts these to a classification problem where labels are zeros and ones. If we want, we can do this ourselves, but we can actually provide this array of booleans. Something I want to also mention here is that, so if you look at this petal width that we use, it might not be very easy to see here, but these numbers in this column are actually from 0 to 3. So you can look at, for example, the mean and max, or use the name of the data frame describe to get some descriptive statistics information. So our goal is to kind of see, if we can find some patterns where a flower is in the given type or not. So in this case, we create our test data, elements from 0 to 3, And we're going to reshape this to a column vector because remember, when you want to pass a data matrix to a linear regression or logistic regression model, even though you have one column or one feature, you need to make sure that this is indeed a 2D array. And the nice thing is that since this logistic regression model by default is a probabilistic model, you can use this method called predict underscore proba. So this will gives us probability scores. So let's look at this. If you look at it, so for each test data point or new data point that we have here, that's like one row, we get two numbers. So the first one is the probability that that data point belongs to class 0. The second one is the probability that it belongs to class 1. And therefore, the sum of the rows must equal 1. So you can see that this first one, we are very confident that this actually belongs to class 0. Whereas if we go to these last few rows, we are very confident that it belongs to class 1. So what we're doing here is that we're looking at the second column of this probability matrix that we have here and see which ones are greater than 5 or greater than equal 5. And in this case, we know that these are the inputs that make sure that we get labels as true, right? So the first column here technically corresponds to false, and the second one corresponds to true, meaning that it is actually this virginical class. And that's what we do here. So you can see that here we have this decision boundary. And you can see that if I plot this, so the first element here is this 1.65. So this means that anything greater than 1.6516, so this number is actually this virginical class. And this is the case because you can see that this is exactly this 0.5 probability. So if we have exactly on this point, we are like 50-50. We are not confident at all. But if we just move slightly to the right, then we are getting more and more confident that this input feature, this petal width, for example, 2.5, belongs to a flower with virginical type. So therefore, this 1.6 here is our decision boundary, meaning that if you're on one side, it belongs to one class. If on the other side, it belongs to the other class. And the reason I like to show this figure here, because you can see that the sum of probabilities for any x, if I add this point and the corresponding point on the other curve, we should get 1 because the sum of probabilities must equal 1. And we can explain the code a little bit too. So one part here in the code is to plot the probabilities that this input does not belong to this virginical class. So that's why we're looking at the first column of this probability. Then for the part that we want to find probabilities that it belongs to virginical, we use the second one. And then we plot the decision boundary here. So now let's look. So remember this X new that we created here was to get this very nice representation of these probability changes, like between from 0 to 3, we see that this probability goes from 0 to 1, and exactly 1 minus this is the other probability, right? That's why we talk about the fact that when we have binary classification, the sum of probabilities must equal 1. But here we do actually have some test data point that we set aside in this case. And you can see that we can pass this X test to this model that we trained and compare the labels that we know given in Y test to what our model predicts. So again, recall that logistic regression by default gives us a probability score. And we look at probability scores for the first 5 testing data points. You can see that these are the values. So for example, the first one is more likely to belong to class 0 or false. The same thing here. You can see different probabilities. Like last one is like 72% technically belonging to class 0. But if you want just the labels and no more probability scores, you can just use the typical dot predict method. So if we do that, so this means that the first data point that we have here belongs to class false, meaning that it's not virginical because it's has higher probability for the first column. The same thing here. And then for the third one, that's you can see is more likely to be in the second column, which that's the true, and then false and false. So remember, the first column is false, the second column is true. And this is because this is how we provide our y's, right? So it's false and true. So therefore, we have like 0 and 1 or false and true. And very similar to linear regression and its implementation in scikit-learn, the best way to understand more about logistic regression is to look at the documentation page. So you can see that here it's part of the linear model module. Then you can see that we can use penalty terms. Now we know what these things are because we talk about regularization and adding penalty terms to loss functions when we talk about linear regression. And you can see like different methods and attributes that we have. For example, if you want to find theta, you can look at the coefficients of the features, all right, in your decision function. Obviously, this is like, an array of size and features. When you have like, let's say, in the case that we have one feature, this is only one. But in case if you have a d-dimensional vector, we have a d-dimensional array. We can find the intercept as well. So we have the intercept. And also you can see more information here about different types of optimization problems that can be used here. And something that is very important to remember is that, all functions implemented in scikit-learn, they come with very nice examples. So this tells you that you can use either .predict to get labels or predict_proba to get the labels, and some other ways that you can access different information about logistic regression.